I have a sequence of random variables. So let's denote that again as x1, xn, like that. Okay, and we don't know anything about their distribution or anything. Okay, they are completely arbitrary. But to make things simple, let's assume that each xi's are taking finitely many values. Okay, you have a finite state space that makes a lot of things easier to understand, but it's not restricted by that. I mean, the result that I'm going to state now, it doesn't require that. You'll see that in a minute. Okay. Now, suppose from this I create a new chain as follows. I will define my y1 equal to x1, y2 equal to x1, x2, y3 equal to x1, x2, x3, yn equal to xn, and like that. So you see, as n increases, the definition of y involves more and more variables. Okay. So if I am now looking at this y chain, how do I describe its state space? What will be the description of its state space? So x's are taking values, so all these xi's are taking values in some finite state space. So A is finite. So how do I describe the state space of the y chain? So it's all finite sequences, right? That's the state space. Do you see that on that state space, that is no longer finite, right? It's an infinite. It's actually, if A is finite, that will be a countably infinite set, okay? Because you are looking at only finite sequences. So these y chain, do you see that that's a Markov chain? No matter what the original distribution of the x's are? That's a trivial exercise. Because if I tell you yn, that means if I give you yn, then there is no point in giving y1, y2, y3, because yn contains all the information. It's complete history. So some people call it the complete history process. And this complete history process is always a Markov chain, by definition. And what is the original process? Original process is a function of the complete history process. So any process you can describe as a function of a Markov chain. This is a very classic result due to Frank Knight, and the proof is extremely simple. So now comes the question, then why do we study anything else? Can we not study just functions of Markov chain? The answer is no, because if you think about, this is, well, in theory, yes, but for practical consideration, if you want to model your data, and if you are using that as your model, just imagine how many parameters you will need. You'll be needing too many parameters to model the process, because the state space is large. And as the state space increases, you will need more and more parameters. So practically it is useless. But it's a beautiful result which shows the power of functions of Markov chain. So now I think the question is that how you can model your data as a function of a Markov chain with fewer number of states. That's sort of the basic statistical problem. Okay? Because anything can be approximated as a, or anything can be represented as a function of Markov chain. Only question is that whether we can make that state space approximately finite. Okay? So you see some basic tools, or sort of, you see the power of this concept, function of a Markov chain. Okay? Anybody has any question about this? Anybody wants me to explain this? Is it clear why anything under the sun can be viewed as a function of a Markov chain? Is it clear to everybody? Because of this complete history process. So this is a result due to a famous probabilist, Frank Knight, who proved it long ago. I don't remember. I mean, this was some of the early results in probability. Okay. So now, if I want to study something like the limiting behavior of the chains, etc., and if it is a function of a Markov chain, then it's enough to study the limiting behavior of the Markov chain. Because if it is a function, it's like if xn converges to something, the function of xn will converge to the corresponding function, and that sort of results will be coming. Okay. Okay. Now, those of you who are familiar with the various limiting results for Markov chains, some of these things may not be new. The results may not be new, but the approach that I'll be giving you will probably be new.